full kind of makes it much more personal and fun. We'll spend a few minutes just on the assignment. I don't know how many of you've done the FRDPARRC. Yes, I saw last night a lot of them poured in, which I haven't had the chance to look through now. But we can just spend a few minutes. Anybody wants to spend time discussing their FRDPARRC in the class? Volunteers? Yeah. Can you tell me the title of yours, and then I'll just join on Slack and it'll be there. No. Just when I search for it on Discord, I was just gonna share the screen. Or if you just remind me your name. Chloe. Okay, heavy metal removal, right? Okay, so I'm just opening that file. And I am just connecting, and I need to mute here and not join the audio. Otherwise, bad things happen. Okay, perfect. So we're just going to spend a few minutes looking through a few FRDPARRCs, just so that everybody's on the same page. And as I had said before, now it's about time to get started on projects. And as you will see, it's a phenomenal way to essentially structure your projects based on FRDPARRCs. So, Chloe, I don't know if you want to walk through, maybe just describe the problem that you're excited about. Yeah. Mm-hmm. Mm-hmm. Mm-hmm.
There's a lot of them, and a lot of ideas, but then after last week, I was thinking more about like, do I even have the resources to actually measure heavy metals?
Mm-hmm. Mm-hmm.
So this FRDPARRC is more like focused on, I guess, alternative ways of measuring heavy metals, like specifically volatile metals.
Mm-hmm. And also, does everybody have the FRDPARRC? Can you all open, just go on Discord. You can see through this more specifically. So first of all, I mean, it's a phenomenal problem. It sounds like this is something that you should build a team on. If you're, I mean, if you've been thinking about this for a while. The reason I'm mentioning this, it is high time to start building teams. It's valuable that you might find also local partners itself. Once I know roughly what you guys are navigating on, then I can find entities in our network, just, for sets of folks that actually need on the ground help as well. But the sooner we do that, the better it is. So just overall, next week we will kind of force teams to happen. So this is about time that you naturally form. Okay, so I see kind of on the functional requirements is detect heavy metals. You have to explicitly state which particular heavy metals, and that can be in the design parameters, because you might have a wish list that's very long, but you might just say focus on mercury. Eventually just say, okay, I can't handle all of it, but let me focus on mercury, but you listed all of them. I see the cost as a criteria. I see the educational context. That's a phenomenal functional requirements, because who's it going to be hands off, right? Do you want a solution to be government monitoring? Then you don't have to worry about the educational context, but if it is in the hands of a community, you have to think about that. Scale is definitely a requirement. And then I guess thoughts are just thoughts. Yes, yeah, that's good. You can always have a line that just says, I don't know where to fit this. And we can actually look through and think about this and see whether it fits in your framework. I think very clearly in the design parameter is the sensitivity. So you've already done micrograms per liter. This is one of the biggest challenges, for example, because it might be that we also know the requirement for what is dangerous for human exposure. And so you have to build something that correlates with that, because WHO, for example, has published data on this. So you could use that as a benchmark to say that I want to be in the ballpark, that if it is twice as high or just exactly at the limit that WHO says is a safe limit, I might want to set up the number associated with that. And then in the context of ideas, as we were talking about this, are there certain class of ideas? So I see an imaging-based idea. And so the way that I would write this one, for example, instead of narrowing on planktoscope, which is technology, but that's a word, I would just say kind of flow-through imaging. It just generalizes it. And again, because planktoscope is already there and accessible as a tool, then you can in brackets say like the planktoscope. Because the implication is that even if the planktoscope currently doesn't do it, let's actually build the capability to do it. And there lies a really interesting idea in what you're referring, because you're thinking about an imaging technology which is now becoming ubiquitous, but you're also looking at something that is at, not directly visible. And there lies the bridge. But that's actually pretty interesting to think about. And there is an analogy to when invisible things become visible. There is one more place, which the whole class we will spend time on today discussing. You've all used that tool where you detect metals or things that are smaller than the wavelength of light, but you detect them with light. I'm wondering if anybody can guess the topic of today's lecture, basically. It's something you use every day, or almost in COVID times we were using often enough. The actual object that you're detecting is much smaller than wavelength of light, but something happens to it and then it becomes visible. I don't know if anybody on the online can guess what I'm talking about. So the challenge that's in the FRDPARRC is, this is written as an idea. The idea is wanting to detect heavy metal, but using imaging as a technique. Imaging is pretty hard to do below 200 nanometers of, we're just discussing FRDPARRCs, below 200 nanometers, right? But could you do something? So could you do a reaction of some kind? So the classic analogy is precipitates, right? When you detect precipitates in reactions, you can precipitate a heavy metal out. And that is actually a classic. There is a lead test associated with that. That depends on precipitate of lead. But those precipitates are still very microscopic. So you still need a technology to be able to detect that better. And so you could then think about, oh, imaging might be one. And the idea that I was referring to is the lateral flow assay tests. The strip of line that you actually see is an object that's way below the wavelength of light. It's actually gold nanoparticles, for example. They can be 20, 30 nanometers. But because they cluster and clump together in very specific ways, then they build objects that have an optical resolution that you could see. And so suddenly you can be sparked and say, oh, wait a second. What is the actual form of this? Is it in solution form? Is it actually, many contaminants can be in nanoparticle forms, for example. And you might then start thinking about, could I actually exploit something that I use from RDTs to make something visible? And again, the trick here is to list as many ideas as possible. And so I think you're hinting towards that, but the way that I would structure it would be so when you say potentially an optical approach, try imagining that, so precipitates would be one way. So then have precipitates as one criteria. And precipitate chemistry is very common. It's used, so lead would be a place to start. You could look at lead precipitation chemistry. That's been done for many years. We have one project in the lab where we are looking at lead in turmeric. I don't know how many of you have been following this disaster. So in Bangladesh and India, there's a massive amount of lead contamination that's been detected. And of course, Steve Luby's lab here has been heavily involved in the uncovering of that, but there is no true low-cost test. If somebody is excited, this would be phenomenal. There's a graduate student in the lab that's been working on this space, and it's related to this problem. But I also know there are many students connecting from India, so please be careful where you buy your turmeric from. So lead in, everybody knows what turmeric is, right? Yes, you all, I mean, some of you use it. So why is there lead in turmeric? So any
Biomagnification.
guesses? Why are people
Is it like,
actively mixing
is it
lead?
like, is it an adulterant, like,
Sounds like a really bad thing.
like an adulterant? Maybe lead.
No, unfortunately, we're mixing it. Yeah. Yeah, something related to that. Yeah, I think you're right on the track. There is something about lead that you all know that has a huge history in even United States. Remember we used to paint houses with lead? What was that? Lead chromate, yellow color. What is turmeric? Yellow color. The more yellow your turmeric is, you think it's better. And so unfortunately, lead is being contaminated. And again, it started somewhere and then people didn't realize. And at this point, there's a massive amount of lead in a lot of kids in Bangladesh. That's when it first got reported. And for the longest time, many people didn't actually know where this lead was coming from because, you see that kids have lead and that's it. I mean, how many environmental factors would you start measuring? And after many years, it turned out that there was a malpractice associated with coating your turmeric roots because turmeric, as in roots, sometimes doesn't have to look really, really bright yellow, but it's still a pretty good turmeric. But in the market, to sell it, people started it all trying. Again, this is kind of one of the tests that we have been building in the lab. So anybody who's interested in heavy metals, this is one. I think I had already mentioned gold and gold mining. This would be another phenomenal one. I could see a little bit of a subgroup around heavy metals, which could try to tackle this in 3 or 4 different ways. So I think having these umbrella groups will also be fun. I'm just posting it as this would be a phenomenal project that I would love somebody to pick up. We have in the lab lead contaminated turmeric. We keep it separately in specialized boxes and all that stuff, so it doesn't make it into some food supply. But we have them from vendors around the country. And again, there is also a test that we have developed, and it would be fun. I saw a raised hand. Was there a comment, question?
It was more of a comment that is lead chromate
Sorry.
cheap enough? Can you hear me?
Was there a hand raised, Pawan, or no?
Yeah, I was just commenting that is lead chromate cheap enough to actually
Okay,
contaminate
no
considering
hands.
turmeric is so.
So let's go back to the FRDPARRC. I got derailed. I'm sorry. I'm just excited about heavy metals. So I think, yeah, one suggestion just for everyone is make it feel like, yes. Oh, can you guys not hear me? Yeah.
We can hear you fine.
I see. Pawan, just raise your hand if anybody has a comment.
Yeah, no, I had a comment regarding that. Is lead chromate cheap enough to be actually be used as a agent to color up
Or they can
turmeric?
just type. I'm going to keep going. Yeah, so a comment on your FRDPARRC is expand it further because this should feel like your idea board. And we'll talk about idea boards in a second because we are going to start that very soon. This should feel like you should be allowed to throw as many potential ideas at it, but make them granular. Like even in an educational context, for example, you can have a massive list of these because it might be that you will only tackle one single row of all of this. Like it can feel overwhelming and you might just say, I first want to really tackle what does a product around this educational context for this looks like. But you have this massive spread of things. And I saw a couple of people on Discord posted they are overwhelmed. Every problem that they start with is connected with some other problem and they don't know where to start. This is exactly the place for it. Spread it out, write everything down, and then you can focus on one. So for example, I would write in terms of the educational context is to raise awareness of anthropogenic impact. And in that, I would explicitly write some approaches that you might take, right? One approach is, how do you make someone believe that heavy metals are bad, right? And then it comes down, any ideas? How would you make someone believe in, say, a community? Can you say something about the community? Like when you say, I can't pronounce this. How do you, Sochi, Milko. Okay. So no, that's good. That's good. Yeah. Sochi Milko. So what is the community? Uh-huh.
Other activities, like
Mm-hmm. Mm-hmm.
and so there's like this organization that's kind of like some, I guess,
Education. Yeah. 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 So again, immediately it tells you the context a little bit, like you're surrounded by water, right? To a certain extent, wetlands have that. And then immediately you can be thinking about a structured activity. You know, one potential example could be is that heavy metals also have impact on fish and other life forms. And that might be an amazing way to teach people. If you can actually find a specific life form, say, I don't know how many of you know the history of when people started finding mutated frogs in the United States. You guys know that history? Does anybody know the five-legged frog story? Okay, I have to tell that story. So again, going back on education, mutated frogs. Contaminants. You know, many of you already know this, that we didn't have the kind of rules, and EPA even didn't actually exist for the longest time. And to a certain extent, there was a massive movement around Rachel Carson and her book when it came out, Silent Springs. That's when we started realizing that just dumping chemicals, any industrial growth doesn't imply you start dumping. That's when laws and rules came about. But the images that transform people's thinking around it are these mutated frogs. They were very sensitive to some of these sets of compounds. And I mean, anybody who sees that, you can see there is a problem. And often enough, you know, you could think about an educational program in which you can find a certain set of species, and then although you're not just throwing books at somebody, you're actually providing a class of evidence. And so I want you guys to go much, much deeper in your FRDPARRCs, because if this document is not filled with ideas that you feel like, oh, I could even pursue 10% of them and then lead to something, then you're leaving a lot on the table. Yes, Henry.
Sorry, I was just gonna ask.
Yeah.
Do those frogs mutate in the same?
No. I think it's just the leg deformities are very common. There's all kinds of other mutations that was found. But what I was referring to, and again, you know, not all mutations have to look so visual, but those images stuck in people's minds. That was a transformation, both in writing and those images transform people. And so when you're thinking about an educational project, you have to be thinking about, how do I convince somebody? It's a pretty subtle thing. Lead, for example, is a tough one. With lead, it's slow poisoning, it's slow growth and development. So for kids, for example, it's very hard to say, but then 10, 20 years down the road, you really see massive impacts and changes. And so again, thinking a little bit about if it turns out this heavy metal and education is the criteria. I'm not saying, I think it would be phenomenal to choose any of those sets of things, but in terms of detection technologies, I would expand. In terms of the educational technologies, I would massively expand. This is literally one of many ideas you could think about. Okay, I think that's all I want to do in terms of spending time in FRDPARRCs. We could open a couple others. I enjoyed reading yours, Henry, last night. I'll go through and start reading all of them. This is, if you are excited about building a project on what you're thinking about, then mark that, share that with, I mean, of course, it's all publicly available, so everybody should write comments. And again, remember, I don't know if I had said this before, the principle that we use is a and principle, not a but principle. So you're allowed to provide critical feedback, but in a positive light. So the approach should be is this is phenomenal, and here are the set of things you add to other people's. If you want to take somebody else's FRDPARRC that you really love the problem, but you have a totally new approach to it, just massively right. It's perfectly okay. We're sharing ideas in some sense, and somebody might bring an insight into a problem, but a completely different person might bring a solution. So again, sets of folks that are listening in, it's a phenomenal way to practice how to develop projects. You will not have time to focus on all of them, but FRDPARRC, you can literally spend, it's an idea generation machine. You can spend half an hour to an hour on any problem, and you will see your own potential of how you think. So this is a little bit like practicing how to ride a bicycle. So don't just worry about your FRDPARRC. You might get thrown in a totally different FRDPARRC that you actually have technical expertise on. You might pick that up. And this is why I'm kind of doing this all in the open. So folks should try writing 3 or 4 different types of FRDPARRCs, even if you will end up choosing one. Okay, let me screen through just one more time to see if an unusual problem pops up. Climate models, I absolutely, whose is that? Can we open this for a second? Let's take a look. Remember, we had discussed a little bit about the idea that climate models are all averages. So let's take a look. So functional requirements, methane detection, network, cost, non-invasive, longevity. And then I guess, oh, is that the problem statement in some sense? Mm-hmm. 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 Yeah, so the broad idea would be is low-cost methane detection. Lots of people are thinking about it. It's a phenomenal place to start. And then you want to write down every single requirement. The first one is it has to detect methane. And then the design parameter, what I would do is make that more quantitative. So I think what it doesn't say is how many parts per million or billion do you want the sensor to be able to detect? Because this will guide you in choosing what technologies work or not. Because you can come up with like, oh, I have a ultra low cost idea, but if it doesn't meet the criteria, it's not meaningful, right? So I would kind of expand on that here in terms of detection. I would put an explicit cost specifically around, because you mentioned Africa, you mentioned wetlands. You can think a little bit about how large that landscape is. What is the density of sensors do I need? You can write some of these things down. And again, this is why much of this is also connected to by the numbers. And so I think this is phenomenal, and it would be fantastic to just kind of you start seeing in design parameters, you start seeing numbers. The moment you start seeing numbers here, then you have a way to evaluate in the analysis. Is that a specific idea could be compared against? And then I'm wondering, So for example, I see the analysis would be comparison, and I see the idea here is hidden somewhere is biosensors, right? Yeah. So I would lift this up a little bit. I would kind of in the design parameters create separate categories. And then even in the biosensor, divide that up into 3 or 4 different kinds. You can think of bacterial sensors. You can think of, you know, an ultra-sensitive cell line to methane. You can, I mean, it's not even crazy. There are, you know, we train bees on detecting TNTs. So just try expanding that massively, even if it sounds crazy early on, because you'll be able to rule them out quantitatively. And I think sometimes in a FRDPARRC, because of an interest that you might have, it's perfectly okay to expand on something that you are excited about. Okay, I think that's all I want to say about FRDPARRCs. I'm assuming this gives people an intuition. Please try to spend time on these FRDPARRCs, because without that, there is no way for you to feel, and I can't judge if you guys are kind of making progress. I love the sets of questions. So I think it's folks are on the right track. And again, you know, try doing 2 or 3 of them, not just the one that you're excited about. Okay, I think we're going to transition to what I want to cover today, which is mostly around paper. Is there any question on FRDPARRCs before I jump? Topics? Nope. Okay, so 2 quick things. FRDPARRC assignment is due today, so if you haven't turned it in, please do try to turn it in today. There is a channel that we just created called Idea Boards. It's a free flow channel that allows you to recruit people. So please start that now. By next week, Tuesday, we are going to try to have a semblance of a team, a rough idea for a question, and then people sharing, this is what you want to spend the rest of your, how much time do we have left? How many weeks as a countdown? Huh? And how many weeks do we, 10 weeks. Okay, whoa, we're halfway point. So that's kind of scary. And I think it was necessary to do all of this, but from now onwards, you know, I can throw a lot of content at you, but what I would much rather like to do is take all our class time in actually tackling problems. So the more you bring on the projects, the less content I will throw at you, and we will just spend a lot more time one-on-one with teams trying to do something, because that's the spirit of the class. And we are a small group, so it's actually fairly easy to do something like that. So the idea would be is this week, I'm going to open up slots both for folks that are online and everybody here. Wednesday, I can carve out the entire day. We can sit down together. You can come one-on-one. You might already have some idea of somebody else that you're pairing with. Pair-ups can be either with folks that are online. They can be local. You guys decide whatever works for people. And then, but by Tuesday next week, we're going to try to at least say, you're totally allowed to jump ship. You're totally allowed to change your project. But it's important to kind of say, this is where I want to start. And how many folks in the room already have a vague idea of what you would like to do for your project? Yes? Yes? So I'm seeing maybe 3 or 4 people as yet don't, right? Are you gelling on something or? So also it's, remember, you guys can recruit these people because you don't want to do projects alone. So folks that have not committed to something, it's fair game to give them a hard pitch right after this class to say, hey, let me tell you about a problem. It's perfectly okay. Show of hands online, folks that feel that you guys have projects or project ideas. I know Khan had a pretty specific project. So just share of hands, how many of you roughly have an idea that you feel you're about to commit to? I'm not saying, I only see Pawan. I know he's excited about X-rays. I see Khan. Avinash, what's the space that you're excited about? Do you want to just say a word?
I Hello. So I was thinking
Oh,
of measuring.
Avnish, I think you're muted. Oh,
Hello.
no, of course. I haven't turned it on.
Yeah. So am I audible now? Yeah. So I was thinking if of measuring antibiotics, pesticides, and heavy metals in the food. So yeah, and I was thinking of it, and I'm yet to build on it. And yes, through the model you shared. Yeah. But this is roughly I'm interested into.
Yeah, so what I would suggest is literally go on the idea board here uh, and effectively write something that you are roughly excited about, and suddenly the commonalities would lead to, so project design boards, post something here, and you will get a chance for what others are thinking about. It's perfectly okay for it to be a rough amalgam of what you're thinking. But do that now, especially because we're going to try to initiate and start projects this week. Okay, that's
Thank
all
you.
I want to say. I'm going to switch to talking about paper for a little bit today. Paper is awesome. I love paper for many different reasons. We're going to pass some paper around. It's probably the most profound technology that we take for granted. I'm sure you've all played with this as an object. And the assignment is, at the end of the day, this week for the lab, try making something unusual out of this object. Anything. It can be an art piece. It can be the most robust mechanical object. So first of all, take your paper and see if you can tear it by just holding on two ends. It's cheating if you crack it, but see who can actually. So what I just did is I want you to all hold a piece of paper. Tell me who's the strongest in the class. You have to hold it and see if you can rip it, but you're not allowed to tear it on the edges of. Oh, okay. All right, one person got it. I wish I had seen it. I didn't actually see it. That's pretty cool. There is evidence. Okay, so others should also just try it. So you got it? There might be something that's happening that you are gripping that's causing the folds to occur. So does anybody know how much weight could a piece of paper hold? What's the limit? So I'm just trying to tear it as much as I can. And if I make sure that my edges here are not causing a rip, which is what is called crack propagation. So paper is not, it doesn't hold cracks. But it's, I mean, it's insane to think about. This is called tensile strength. And you can Google it and see how much that might be, or you could set up a very simple test in your home. If you have dumbbells or something that you work with, try coupling it and see what is the maximum weight a piece of paper can hold. And I'm telling you, you'll be surprised. So, you know, it is a remarkable object. There's no need for it to be that strong, but it is. What other things do we find remarkable about this piece of paper? Yeah. We will think a little bit about it. That's a very complex question because, and I think partially not so well understood, because, you know, it's made out of fibers, cellulose fibers. We'll talk a little bit about that, but they are entangled. So when we talk about macroscopic properties of materials, we don't have very good theories of entangled matter. We have good theories of solids, and if it was made out of a crystalline structure, I could tell you from that crystalline lattice what the tensile strength from first principles would be. We don't have very good first principles of entangled matter. There is a scaling law that people have been playing with, and maybe I'll see. I don't think it's here, so I should just pull that out. Just strength of paper PRL scaling law, because I could experimentally measure, for example, for different types of thicknesses, different amount of entanglement, and I could see how it scales with thickness. but that would just be an empirical law. We don't really have a theory, and I'll see whether there is a scaling law that is yeah, not this paper. So you can see that they're doing basically, and that's 2015. So it's actually paper, not that paper. I think it thinks paper strength, cellulose paper strength. There's a very beautiful scaling law paper that I just want to show you. Strength of oriented, talks a little bit about, okay, entangled fiber networks, mechanical strength. And you can see that they would have many different properties based on the kind of bindings. And so there is essentially a binder that's used. So it's not by itself just the cellulose fiber itself. There are also the binding components. I just want to show one picture slash figure. So, you know, something that you'll see is many of these sets of things, if you were to do an SEM on this, there's a lot of air in it, right? That's why I can see through it. You can, there are pores in this. This is why it can soak stuff. But then there is also binders. And those binders are what couple the fibers together. They don't allow them to slip. That's why cotton, for example, you can shear, paper you can't, because the binders, there are polymers that are actually used to make this thing. This is also bleached for that matter. So there is a lot of very interesting processes that have gone in that give kind of the mechanical strength of paper to begin with. And again, I think the whole reason I'm just talking about paper is I want you to explicitly think about objects around you as incredible properties that they hold and subtle things that you could potentially then utilize, right? So one assignment, for example, if somebody wants to do a bonus, the assignment is make something interesting out of paper, but a bonus assignment would be is make a machine that moves around using paper only. So I'm thinking, Henry, you're thinking about it. So that would be fun. You would stretch its limits of seeing, oh, wait a second, my motor has to be made out of paper, my actuators have to be made out of paper, I want to make an actual machine that does something purely out of paper. So another really fun thing, so hold your piece of paper, and then I'll get to it, Khan, for a second. And I want to show you something quite surprising that happens. So, you know, if I'm holding it, this is like the cantilever test. I want to test its bending properties. It's quite thin, and you see it kind of bends this way. And then it bends the other way too, right? And now we'll pay attention to how much does it bend. So I can see, and I think this is best done with, yeah, you do want the fresh paper that doesn't have crease on it. So I'm noticing it kind of, it flops this way, and we don't have a square piece of paper, right? I'm going to try cutting it square because that test is a little bit unfair. But let me see, if I was to remove the asymmetry in the length of the cantilever, let me try that again. So I'm just taking a piece of paper and bending it, and you see it flops to the side, and then I just rotate it 90 degrees, and notice right there. Do you see the difference? it's not flopping as much. I'm going to rotate it 90 degrees, holding the same way, and boom. Do you notice something? I'll do that again. It doesn't flop that much. Why would that be? So look at this again. I'm holding the same piece of paper. I've roughly made it into a square. I'm holding it at a point, and if you look from the side, right there, it doesn't flop. And then if I just rotate 90 degrees, boom, it flops completely. Right there. Do you see that? Okay, so what's going on? Yes. Exactly. This object that you think is isotropic is not isotropic. And why is it not isotropic? Because it's actually made in a mill that runs through in a specific direction. So in the process of going from wet cellulose to dry cellulose, somewhere in there, that anisotropy or that alignment has been embedded. And somehow that alignment is connected to strength, but we can't quantitatively write down an equation and tell you the degree of alignment or order parameter and how it connects with the strength. So I think the exercise associated with this is suddenly if you're going to use this for something, you could take advantage of it. You're getting all of that for free. You could think about this as an anisotropic material. So similarly, there are many interesting optical properties of this. We use this in Foldscope for making a scrambler, because when the LED lights come in, they are a point source. And for illumination, we don't have that much distance for a condenser. So we essentially use this to scramble light. And again, you know, this is kind of way of thinking about a filter, that light bounces back and forth. So what comes out is quite diffused, and it's uniform, even though initially you don't have a uniform light. So commonly in optical instruments, you try to collimate it. That requires another telescope to expand the beam, make it uniform, or you could just use a 2 cents of piece of paper and suddenly you have an optical property. Where else do you think we use this object beyond writing? There is another couple of other locations we use paper for other properties too. Other things that people have done for the last 50, 60 years. Somewhere in health. Is there a health product that's made out of paper? Yeah? Say that again? Scrubs are made out of non-woven. They are kind of in that same class, but many of them are also plastics, which are problematic. Yes. What was your name again? Yes. Diagnostics, exactly. RDTs are all made out of paper, actually, and we will talk about quite a lot of that. And again, it's using a very specific property. It can pump fluids. It can hold and bind many analytes and proteins. It can actually also be used to bind to DNA. So you can do DNA concentration on paper just by the inherent properties of cellulose. Yes. How could we sterilize paper? UV would be a pretty simple one. This is also treated with bleach to make it kind of this off-white color. Not all paper, and so not all paper is made equal. If you're going to build a project around this, think of this as a massive technology that has emerged from around the world, and you need to know your paper if you're going to build on something like that. And I think, again, one of the key things to be thinking about is not take the objects that are there for granted. Khan, I saw your hand for a second. Sorry, I didn't stop at that time. I was deep in my thoughts. Okay, what is
Yeah,
it?
so I just have a question.
Go ahead.
Because you show the paper, it have a different fiber and it organized in specific way.
Yes.
Then we can measure that. So, but I'm the cancer research, so it look at fiber, it look like EMC, like
Yes.
collagen or something.
Yeah. Extracellular matrix.
Yeah,
Yes.
so in the normal and cancer also have a different EMC. So I'm wondering how we can measure that. How
Yeah.
can we show differences?
Yeah, that's a
So that,
beautiful idea.
and we can based on microscopy, we can see the fiber orientation or something else.
Yeah.
So they're not just the component density, that's what we did, but I think maybe the fiber orientation or something else. So
No,
I am
I think
thinking,
that's a
yeah.
beautiful idea. So what Khan is referring to is that there are cancer cells, when they form tumors, secrete a ton of ECM around, and the ECM organizes very specifically to the type of tumor, the structure of the tumor, and could we measure some of those same orientations in some very simple way? For example, if its effective mechanical properties change. Yeah, no, that's a really fun idea. And I think very recently, there are a couple of optical stains that I'll share with you that have been used to measure ECM orientation. It was an accident that was discovered that has now led to a massive amount of growth in imaging of ECM now in both pathologies and other ways. So Khan, I'll send you a couple of those papers. It's a fairly recent insight and an accident that happened along the way.
Yes,
But
thank
again,
you.
you know,
That's
measuring
great.
mechanical properties of certain things could be an insight into microstructure without seeing the microstructure, right? Okay, so let me show you a puzzle that I really like. So you all know the assignment, but we're going to do something very quick. Hope, is there some water that you could just bring over there? And then another thing that would be is if there is a binder clip or just, oh, right there are the binder clips. So I'm going to now do, this is something that I won't tell you what just happened, but this is one of my favorite demos if it works. It doesn't always work. I'm taking that same piece of paper and I am breaking it into tiny strips. And then something heavy that I can hang. So maybe that little piece of plastic. And I'm going to be hanging something down here. But before I do that, I'm just taking a piece of paper. Folks that are online, we're just going to take a single piece of paper. You can dip it in water. And of course, something fun happens in general that you might have predicted, which is, can you all see that water is rising, right? We will talk a little bit about that. This is inherent, but all I'm going to do is just dip the entire piece of paper in. Do you know why paper becomes soft? If you were to pull it now, what happens? Actually, do you want to try it? No, let's have you try it because you're the strongest person ever. Okay, so go for it. Try ripping it now. What just happened? So any ideas? Yes.
Is it that you're washing away the binder?
That could be one. Okay. What else could be going on? Yes. Cellulose is not soluble in water. The amount of cellulose is still there. It's not as if we have removed massively the cellulose. Yes. Yeah, because they have swollen. And so the gaps are changed. There is a lot of water in the pore. You can give that back to me. Yeah. We will play with this for a second. So what immediately happens is that what you think is very strong is suddenly not very strong in a wet state. And it's actually quite a puzzle. It's not so trivial to say, oh, with how much water would that strength would look like. And what I'm going to do now is something, yes. Mm-hmm. A question that you would have to resolve. Try doing that experiment. Some of the strength does come back, but the paper is not the same anymore. Because again, if we are referring to any sets of properties, all those sets of properties are driven by what's happening to the microstructure. We have fundamentally changed that. This is also why people say that paper has memory. Every crease, every fold you made, you've changed the microstructure, so you can never go back. So crumpled paper, for example, remembers exactly how you crumpled it. Okay, so I'm going to do is hang a tiny, I'm just taking a strip of paper and I am hanging a little binder clip to it. And then I will just hang it like I have done on that sheet here. This is a picture that we had taken in the class a couple years ago, and then we will just let it dry. Okay, so, and maybe just for fun to see, I will cut 2 strips, one thinner than the other, and the experiment works half the time, because I have to be careful with the paper. So try it with different types of paper, and then maybe at the end of the class, I am letting it dry, and I'm just interested in what happens to the structure when this process of drying, which you were asking. I mean, some of it could be strength, but I'm not doing a strength test here. I'm actually doing something else. So let me take another one, maybe a second binder clip. Do we have a, when there is one, I was thinking there might be 2. Unfortunately, no second binder clip. Okay, we will just live with the first one. But anybody who's online, try to hang a piece of paper wet and hang it. And it's really, really fun. If it works for you, you will be quite surprised. And you just want to dangle it. Oh, perfect. So we will let it dry now. I don't want it to interact. And yeah, maybe another heavy object. Okay, this is good. And again, I'm not doing this as a careful experiment, but you all can. I just want you to think about it.
You have to not succumb, or rather not.
Can you say that again? Okay, yeah, give it a try. So, I think one of the things that I want you to appreciate is that even such a simple object is actually quite remarkable. There's lots of things that you can think about, play with. In the same category of paper is cardboard, and cardboard has been massively engineered for mechanical properties. And one thread, just fun as a, not going to spend too much time. If some of you get excited, take a look at what people have really done with cardboard. I like this one example. There is a local Stanford student in the design school. There's a website called Cherigami, where he basically makes lots of furniture. There is lots of people around the world that make furniture. This one is really designed around schools and building fast adaptive furniture for schools. This is one of my favorite examples. Some of you didn't probably realize this, that almost every ventilator, when you put people on ventilators, it's being filled with viruses, right? Because the person is sick. So from a COVID context, there is actually a filter that you put to make sure that the machine itself doesn't get contaminated. So you could use that machine with another patient who may or may not have COVID, for example, or some other known viruses. And during COVID, even though there are many machines that were available, these paper filters, they ran out in terms of the manufacturing process for it. And it literally is a filter that has this beautiful origami fold inside it. And they couldn't figure out how to make these fast enough. So we were thinking quite a lot about simple ways of manufacturing. And the trick there is the paper was trivial for them to make. How do you seal it? And again, you can see it's massively folded. That implies it has a very large surface area. And these are called PAL filters. That's the one company that makes this. And so many people make the ventilators, but there's a bottleneck associated. And then these are use and throw filters. And so effectively, people panicked because we just didn't have, so many machines were out of commission because they didn't have these replacement filters. And the challenge there was, how do you seal at the resolution of the filter pore itself so that you, and it's actually a non-trivial thing if you think a little bit about it, that even when you make a filter, you have to make sure that it seals with something that's non-porous. And that's why the manufacturing is tricky. Another fun example of paper that I actually like is somebody thought that it would be fun to actually throw an airplane from space, paper airplane. I saw you made one. So would you think it would survive entry into the atmosphere? Yeah, so it's a puzzle, it's a tricky question because what velocity would it pick? So first of all, they did a lot of tests to figure out the thermal resistance of paper. And this is also why it's fun. Like sometimes you get excited about a scientific idea and you just go explore. So there was a massive number of tests that were done on thermal resistance. And the February test on the prototype was a 2-inch by 2-inch plane. It survived Mach 7 speeds and temperatures of 200 degrees Celsius for 10 seconds. And I mean, that's remarkable to really think about what cellulose could actually do. Yes? Mach 7 would just be like 7 times the sound barrier. So the sound barrier is 300 meters per second, 330 meters per second. So Mach 7 would be 7 times, I think. Yeah, which is insane to think about. That's the entry velocity. And the idea was if you are on International Space Station and you toss a paper airplane, will it survive? And again, it's not a crazy idea. If you want to bring very low cost mechanism to bring something into the atmosphere, that would be useful. The only problem is if you do the experiment, nobody can find the paper airplane. So that's why they didn't do that experiment. But it is feasible if, for example, we had a detection technology that entry into the atmosphere done for things like these could actually be made that way. And again, it's not as if there has to be a function to it. It's really fun to even know what the limits of a material that you might be using is. The other thing that I'm going to spend a lot more time now primarily is on diagnostics, because the lab this week will be diagnostics. But I just want you to mention, just explore how much people have really expanded what you can actually do with paper. So I think that's kind of the prelude. I could spend hours and hours. I love many aspects of thinking about, making musical instruments out of it. And it's a practice in creativity that restrict yourself to only one material and see how much you can expand. This is what artists often do when they're trying to find their style, when they're trying to do something new. It's not the opposite, that think outside the box. It's actually think in the box. See how many different things you can make out of just the same object itself. So it's a little bit of this framework that is useful while you're trying to explore and expand your creativity. So just see how many different things you can make with a piece of paper. Okay, I want to mention something about tests. So the history of this is just really remarkable. And, of course, we are very commonly thinking about litmus test. You all have done a pH test before made out of paper. And that test goes all the way back to the 2040s. This is Arnaldo. And one of the things that they actually realized at that time is lichens had certain sets of compounds that were pH sensitive. And around that time, they started using lichens as a mechanism or a way to be thinking about running as a pH test. So, this is one of the oldest analytical tests that's known. And when I read it, I found it shocking that it went way far beyond I would have thought that it would go. Because at that time, alchemy and all that stuff was very, very common. But still, people just thought that, wait a second, this thing changes pH. There's a lot of other food products that actually change pH. There are, I don't know if you guys have played with the purple cabbage. When you take fruits, does anybody know why fruits turn brown when you leave bananas or apple? So the question is, if you cut an apple and you leave it on the table, it turns brown. Yeah?
It oxidizes.
Yeah? Yeah, it's reacting to oxygen. It's oxidation. But then you can ask yourself, what in that process is causing a color change? And again, there are actually some genetically engineered fruits people have been thinking about that don't turn brown. I don't know if we really need them, but that's I think when you have a hammer, you look for nails and everywhere. But I think it's valuable to think about that the history of chemical analysis and the ideas go way back. One of the most beautiful ones in that space, which is at the heart of immunochromatography that we'll talk about, this is an assay that you can run very easily, and sometimes when you paint, it happens accidentally. This was the first set of an example when people started thinking about, and this is now 1800s, that you could separate molecules using things like paper. So the history of all of protein purification lies in that tiny little test, which is you take a paper strip, you put some dots. You can do this because every color that you use is actually made of many reagents. You put those dots and you let water run through it, and you can actually see, for example, this is a really fun one. You can do this if some of you like spinach. Next time you cook spinach, this was actually done on spinach first when people understood that, wait a second, there are many, many components that make what you might think of an extract. So you take spinach, you grind it really well, you get that green color, you put that on the paper, and you let it dip and let water run through, and you would actually see many different types of chlorophylls even can separate out. And then, of course, we haven't said anything. What about the property of this sheet leads to something like that? But they didn't know that at that time. But literally, chromatography and most of protein purification started by just playing with these materials. And this was known to artists for a long while, and many artists actually use this trick. So there are wet color paintings in which you can truly see pigments that are separating out, that are because people are actively trying to. And everybody's seen this bleed through that happens, right? If you are painting on wet paper, you would see this bleed through. Then kind of comes the modern era. And this is something that, again, it's a little bit of a crazy thing to think about. We have known this for a while, but now you can get thousands of different types of papers that are specific to very specific diagnostic applications. We'll talk about nitrocellulose, for example, is one class of paper that RDTs are made of. This is a fun one. It's called the FTA paper. And it's essentially a way that a lot of DNA in the field can actually be stored and still preserved. And so one of the things that's associated is you could just literally, so if you're thinking of a genomic sampling project, you want massive amount of genomic samples to be collected. The most common way it's done is blood spots. And what I don't like about it is that price point, because you'll realize that it's just people taking advantage of the fact that other people don't know this, that almost all paper actually does this. And yes, you can improve it a little bit, but you could also just massively expand and test. And so in some sense, for a lot of genomic surveillance, Whatman paper is a very classic, this FTA paper is used. So for a lot of malaria genomics, for example, the samples primarily arrive as dried blood spots, and you can then do lots of extractions. Yes? Yeah, so I think we will talk about, when we talk about the diagnostic test itself, this is something that we'll think about. I'll show you a video of how easy it is to make your own diagnostic test. I think the only challenge right now is in the biologics itself, making the antibodies and making the biological reagents. But we'll walk through that in a second. So I think just to give you kind of an idea in terms of thinking about this, this is, around in the 1950s, people had realized that there is a ton of frameworks around thinking about DNA binding with cellulose. So the fact that you can use paper for extracting and purifying DNA has been known for a very long time in the biochemistry literature. And one of the fun things that happens is, again, it took a long while, and much of this literature has been out in terms of people have thought really about why is it that there is DNA binding to cellulose. And I think in the, I would say 2017, 2015, there was a really nice paper that essentially explicitly writes this down to show This is a very standard technique for doing DNA extractions without all the fancy things that you can then do with these classes of beads. All you do is dip something and wash it, and there would be explicit binding and more amount of DNA has bound to that paper. And so this paper has inspired a lot of different techniques post where people have really developed the kinds of different types of papers for making sure that you could do DNA extraction. Again, all boils down to that original idea where somebody said, wait a second, I'm seeing this explicit binding, you can actually explain it, but then it took that long for some people to actually exploit that. So that was 1950s and 1970s, and now this is 2017 is when they explicitly show that you can use this for DNA extraction and amplification assays. So it's a little bit surprising that a lot of fundamental knowledge exists, but the barrier often is we don't believe it to a certain extent, or nobody was really thinking in this context of, oh, I need a very low cost way to do DNA samples out in the field. Yes. Yeah.
Here it's binding, and then for paper chromatography, like the separation of molecules, is that like size extension?
Yeah, you can think about it in the context of essentially different molecules are traveling at different speeds because they are interacting to this matrix in different ways. The driving force in that case is just the wetting, the capillary forces that are driving it. In this case, we're not letting it drive. We are just exploiting the idea that there is affinity of cellulose to DNA. And when I wash it, some DNA will still remain. And again, it's a question mark of saying, oh, I now want a better mechanism. Then you can go to different sets of, if the amount of DNA that you're looking for is much larger. But in most of these examples, you're not limited by the amount of DNA in some sense. While the previous case that you saw is pigments traveling, and they're also interacting with the cellulose, but in different ways. And again, I think this is also why we don't just use paper that you buy from a store, because I have no idea what has happened to it. There are surfactants in this, there are polymers in this, there is bleach in this, so this might not be a good idea. So starting with the baseline of, oh, can I find, so there is classes of paper that are very well characterized, and then you can start adding your own components to it. And again, I think it's a little bit about that there is a massive amount of space, and paper diagnostics has expanded. So now this literature over the last 10 years is massive. And all you have to do is, read through, take advantage of it to the function that you care about. But not all functions are still implementable. So we're not there yet to do amplification-based assays. Still, there is beautiful space for all of you to be thinking about. But again, the trick is understanding. The only thing that I want to make a claim of is every object that you take, try digging in deeper. So it was the binding chemistry of the cellulose to DNA, and we take most objects for granted. But if you just look at under a microscope, figuratively speaking, you will find sets of ideas that you could exploit. So that's kind of the balance of what I want to say about paper, really, in that sense. Okay, so let me show you a few sets of things around RDTs. And I'm going to do this in the context of the history, the 60 years history of RDTs. So first of all, everybody knows and remembers, for malaria, we had discussed this, right? I mean, I had said that roughly around 300 to 400 million tests are run every year for malaria alone. At this point, everybody here has run a COVID test. How many of you have opened your COVID test? No? Oh, I had just assumed that. Maybe, is there a COVID test around? You might have a test in the lab. I usually have them in my bags. This might be a good time if any of you have your old COVID test lying around or new COVID test, try opening it because we'll talk a little bit about it. Okay, I'll show you pictures, but please go home and open a COVID test. It's not that expensive, and you will find that there's almost nothing in it, which is the point. But there is actually subtlety of materials that we'll talk about in that context. But again, RDTs have their limitations, but it's very important to understand this technology because the last 60 years of this development, so if you just think about it, That's 2014 numbers, and that's roughly around 300 million. I think right now the number is 400 million tests run. And the reason I'm emphasizing diagnostics and the context for this is I would say less than 2 or 3% of these tests are made in Africa currently. So there is a huge gap between a technology that we have had for 60 years, but it hasn't, the manufacturing of it hasn't made it. And I'll show you how simple it is. And effectively, you know, now that's starting to change, and at least people are taking that seriously post-COVID. But there are still many barriers associated with it. And if anybody is excited about diagnostics, you have to be thinking about manufacturing. And that would be a phenomenal project space to think about. That why is it that when 95% of all burden is in Africa, less than 5% of manufacturing is there? And this was a huge issue when COVID happened, because Abbott decided to use the same lines that they used for making malaria tests for then making COVID tests. And, you know, it's a profit-driven entity. They can do whatever they want. But then that led to a massive scare that we might not actually have the sets of supplies. And again, I've already talked about it. There is lots of problems with the test, but just this is the harsh reality. So we should understand it. We should think about this object carefully. So that's the original patent. I'm excited about you all to be reading sets of patents. There are derivatives of these, but it's fun to read this one. I'll post this patent online. And kind of one of the things that you would see is it's using something very, very simple as a property of paper, which is wicking. That when there are air pores in it, so there can be ranging from kinds of paper, 50 nanometers to all the way to 10, 20 micron holes. And when you add a fluid to it, it will travel, right? That's kind of makes simple. That travels bidirectionally. You can think about, you have components that we'll talk about in a second in the manufacturing video. This is the sample pad. This is where you're putting your samples. This is what's called a conjugate pad. This is essentially where there are antibodies that will pick up this analyte, and they're also labeled. And effectively, there are two lines, which are two antibodies that are control and the thing that you care about. Control binds with everything. This one only binds when you have this sandwich. And then in the very end is just a wick that acts as a pump to make sure that fluid goes this way, right? So intuitively, you carry, if there is an analyte that could be detected, there will be binding here. If that is not present, there won't be any binding here. So this strip will be blank, and this strip will still light up. Does that make sense? Okay, so here is a quiz. Why is there a limit on a test? Why do they say, take a picture in 15 minutes, and then after that, it's invalid? So everybody has seen a test before. Now, why do they say, as a manufacturer, that you have to read out in an explicit amount of time and not longer than that? Yes? The antibody would start binding to each other. Where would they come from? Yeah, go ahead. Yeah, we're just thinking out loud. The antibodies would start binding non-specifically. You know, I think kind of one of the ways of thinking about it is, but where are they coming from? Why is it that once you've run the test, yes? It diffuses, so that's an interesting idea. Actually, the answer is related to that. The process that we are dealing with here, which is this notion that after a certain time, evaporation kicks in. And evaporation, when things start to dry up non-homogeneously, you actually get backward flow. Because remember, this is also, all of this is hydrophilic, and you get all kinds of flows that's not directional So things are basically jumping from one place to the other, which is a little bit like diffusion that you said, but it's not true diffusion. If you write down the diffusion time scales, it would still take too long a time. Yeah, because there is flow that's non-specific. What's nice about this is you try to make a paint of this, but at this point, if all of these, if this starts to dry in patches, which you don't control, eventually there will also be flows that will begin that are uncontrolled. And then you could think about, you're absolutely right, that these things can start landing anywhere. And effectively, wherever this lands is what you think. So imagine if a lot of them just started landing in a manner that is because of that flow. And again, you don't control how it dries. And so you want to make sure that you read the test at the time that it's wet and not anything after. You could try doing this test. Put a camera on it and see if you can see any backward flows after some time. Like, it would be a beautiful time lapse. It would be trivial for you to do a COVID test, put it on, and most likely nothing will happen. But once in a while, you will see this all kinds of flows that emerge. And this is also why you lay them out flat, because there is gravity associated with it that can perturb the sets of flows. So there are subtleties in everything that you design. And it's valuable to remember that although this is a phenomenal technique, it's actually good for when you are bringing, like, for example, there are a number of strips that you can put. But if I wanted to do a type of a reaction that now requires two chemicals to come together, spend some time, then go to step 3, which is isolated, you can start seeing the limitations. And a lot of people have been working on these limitations, and that led to this massive space of what's now called paper microfluidics, which is, oh, wait a second, why do I have to just be linear? And although there are still limitations, but you should still think about it, that finally you can make, and this is something that we could do in the lab on Friday, is to have inside paper things flow but not. Actually, does anybody know how you would make this? So I'm asking a question. On the right, this is from George Whiteside's lab that did a lot of work on paper, still continues to do on paper diagnostics. How would you make that object in paper where you have 3 analytes that could run in a line but not contaminate each other? There's a very simple trick. And once I tell you the trick, you'll all be able to do it. But I'm curious. Yes. How would I make a type of, this is not normal. If you put 3 drops of color fluid on this, it's not going to do this. So there is something that has been done to this paper. And the simplest thing there is that you can make areas that are hydrophilic and hydrophobic. So wax. So what has been done here is wax has been patterned on this in a specific pattern. So I can pattern, if you just forget about one, I can pattern wax all around other than this. And so the water will only wick in that line. That makes sense. And then what has also happened is that they've done it in a 3-dimensional manner. So you can stack pieces of paper, so you can get vertical flow as well. So it's kind of like weaving, but with hydrophilic, hydrophobic sheets. And this requires a wax printer. It's a pretty straightforward thing. We could make this in the lab. You can think about just dripping wax around in different ways. And you can structure paper. And again, I think it's a very clever space of thinking about just that there is a massive space to be thinking in terms of, yes. Yeah, I think that's kind of been one of the things that although lots of people have developed technologies in the space of expanding, they have not been so well thought through in terms of the kinds of things. So I think there are good use cases. For example, urine is a pretty rich analyte. There's tons and tons of thing in it. And you might want to take the same sample, but expose it to 5 different things. Just be collected once. So when you want to do multiplex assays, you can imagine a type of a structure that looks like a flower, which is what is commonly done when you have 6 different analytes, 6 different reactions happening, colorimetric tests that are not just one strip and then you dip the other one. You can do things linearly. I think the most interesting space in this is when you need to prepare reagents on the fly. So for example, with the RDTs, the conjugation step for the antibodies and the beads, the gold particles, doesn't happen on it. It's pre-prepared. But you could imagine cases and scenarios in which you need to bring reagent A and reagent B together, and then after some time, bring reagent C and do any arbitrary chemistry that you might care about. So then some of this plumbing starts to become important. And again, I think it really is a question of a choice. So instead of starting with technology, the ideal place to start is what would you like to do? And then go back and see the bag of tricks. And then, I mean, this bag of tricks is massive. It's phenomenal in terms of how many number of things can actually be done. Mrinal, go ahead.
Yeah, I'm just a small doubt.
Yeah,
I
yeah,
see
yeah.
that I see that we have four colors, and then they're oriented like a U.
Yeah.
Instead of orienting it like vertically and making a hydrophobic layer in between, is it because like it has to travel a certain distance and to make the paper short, like to
No, I
make sure
think
that
this photograph is just for fun. It's to show that you can do something arbitrary and complex. This specifically doesn't have any function, but you can imagine that there are requirements. Just like we make circuit boards, why can't we make paper fluid boards? So it's just trying to show that you can do crossovers. There's no function to it. You could think about interesting functions. You could say that, oh, I am going to have an analyte travel along a different direction, and if chromatography is happening, some amount of whatever is in there is getting lost. By the time it comes back, that is different from the starting point, and I could do some differential measurement. And if I do this differential measurement, it might give me an interesting readout. So, I mean, I could imagine ways to exploit your path length to function, but this is particularly just done for fun. Yes. Yeah. Mm-hmm. Yeah, I think the comment that I'll make is there's a lot of people that have worked in this space. There is sets of people that work primarily on growing technology. Just what is the raw, what can you do? You ask a question, and then you try to do it. There are other sets of people that work backwards, where they say, oh, this is what we would like to do. Let's explore every possible sets of technologies that come together. I'm not talking about anything on the kinds of assays. You know, in the old days, much of the paper diagnostics was specific to non-amplification based systems. More recently, there are some amplification-based systems. Some of them are not true paper diagnostics, that the majority of the thing is still happening in an Eppendorf tube and the readout is happening in paper. So it's the landscape is quite large. And I'm not covering, I just want to give you a hint, and I'm also going to charge my computer. The goal is for you to feel the rough landscape of all of this. And then if some of the teams are excited about diagnostics, we will kind of sit down and I can do a very detailed set of a thing of this is the technology landscape. This is what Hope and I work on. And in the lab session, we'll kind of focus more on the amplification technologies in some sense. But it's just, I like this space because it's rapidly accessible. And on that note, I'm going to first show you how an RDT is actually made. So let's just jump to that. Okay, this is a fun one. I really want to pay for the official.
Self-adjustable glasses are taking the world by storm. They let you achieve a perfect 20/20 vision at any distance.
That ad was actually pretty cool. I was almost tempted to actually listen to it. It's very rare that the ad algorithms work. Uh, uh, okay, since this is 10 minutes, I'm gonna do what I normally do. I don't watch YouTube at normal speed, so I apologize for that, but I want to save time. It's a little bit of an advertisement too, but I do want you all to see. So is where we take reagents, that holds the device for running the test and very quickly and getting the results on the spot.
So I think the example that comes to mind when you talk about lateral flow is the pregnancy test. Infectious disease like malaria or HIV or COVID-19. So let's get started with making our lateral flow test. So step one, we want to prepare in solution tubes of our control line antibody and our test line antibody. That's why you see two lines. So the test line antibody is the antibody that recognizes the thing you're testing for. So for pregnancy, it's HCG. It can be different for different applications. Once you have them prepared in the solutions, you can then dispense it onto nitrocellulose that we have here. And this is how you get the two lines. So I'm going to place my membrane, make sure it's flush to the bottom so that my positioning of the lines is the same from membrane to membrane. And here you can designate the X, the Y, and the Z of these needles right here. First, I want to select and then I hit go. So there's two parts of lateral flow. We're dispensing the capture antibody, and then later we will dispense the detector antibody. So I've just finished up marking where the lines were dispensed. I've labeled the control line where we dispensed our control antibody to ensure that the test was run correctly. And then here, our test line, that's kind of the line that we care the most about. That is where our capture antibody is. And then you would let that dry in the oven for 30 minutes. And then the second major aspect of your lateral flow strip is the conjugate. So what is the conjugate? The conjugate is your other antibody that would detect your antigen and form a sandwich, but on that antibody, we'll have a visual particle so that we can see it. When we stripe on the test line, we can't really see the antibody other than, initially when you dispense. So in order to visualize whether two antibodies bound to an antigen, we need one of the antibodies to be labeled to a visual particle. And this visual particle will dry down and dispense into what we call a conjugate pad. And then later, we will take all of these and we will put them together to form our lateral flow strip. All right, so now we are going to dispense our detection label. And the detection label, we aren't going to stripe like we did for the capture. We are going to spray it so it's a little bit more spread out. So I'm going to disable our front line.
That's where the sample would go.
Since we're no longer dispensing antibody onto a membrane and kind of temporarily storing it. This allows us to keep reagent dry down onto a material and allows lateral flow to be run in various different conditions and places. Traditional laboratory tests, you would need to use a pipette in order to use this reagent. But with lateral flow, we can dry it onto this pad, and then now anybody with a plastic transfer pipette or a dropper bottle can run this test. So now that we've dispensed our detector label, we are ready to put this on a screen and dry for 1 hour. And we're now ready to assemble our test. Our dry dispensed reagents, we have our nitrocellulose membrane with our immobilized capture antibody. We have our conjugate pad sprayed with our detector antibody. And one more part of the lateral flow strip is the wick pad or the absorbent pad. This will allow the liquid to flow from the bottom to the top in a continuous fashion. So what I'll need is this backing card. This is what is going to hold all of the different components of my lateral. Very gently press
Professor, you are muted, I think. We cannot hear you.
Your computer. Okay, can you hear me now?
Yes, Professor.
Perfect. Okay, all I was saying is this is super simple to do, and it drives me crazy why RDT manufacturing is just not so widely available. Because there is nothing technically that's actually stopping us. It just requires small amount of investments, certain amount of desire to bring this capacity much more broadly. And thinking a little bit about if any of you are interested in a project in that space to say, oh, what is the barrier now? You know, is it quality control? Is it antibody production? Is it associated with investment? Is it IP? It would actually be really fun to think through and think about this as a project, as a class, because it's a little bit ironic that so much of the infrastructure around health, and then again, a large number of tests could actually technically be provided on structures like these. And I think for folks that are really interested in diagnostics, Thursday we will cover a technology that Hope and I and Anesta, another grad student, and a few other students who've been helping in the lab have been working on. So it'll give you the first-hand scenario of what does it take to manufacture a test, and especially going through the kinds of parameters that we've put around. But in some sense, oh, wait a second. How do I, that screen is different from the screen that I want to share. It's stuck. Oh, are you sharing from yours or no? Am I sharing? Resume share. Okay, sorry. So I want to leave here today just with this notion that there's a massive space in diagnostics. It is something, if you were to think about the gaps that exist in our society, and the needs are just astronomical. It's also technically a really fun area. It has all the context of enough biology, enough engineering, enough manufacturing, enough social context, enough infectious diseases, that it really brings a lot of fun fields together. And I think over the years, there has been this massive demand of thinking about accessibility and affordability, and that's not baked in our current conventional commercial models. And so it is important to think a little bit about is how do you flip the, I had thought that COVID happened, that's going to massively bring diagnostics to places around the world. And I'm totally depressed by the fact that that is absolutely not true. None of that happened. There are trinkets of what I would say is positive, and then it is upon us to be thinking about this as a challenge to make sure that we utilize that as a springboard to be able to make something like that happen. There's a lot written on that on the equity side of this, and I think in the next class before that, I'll give you guys some reading assignments so you know and understand the diagnostics gap, what a large gap exists in terms of how many, I think the numbers are just absolutely astounding to think about. More than 3 to 5 billion people live on the planet with just not having access to diagnostics. So the number, and again, that is, you can look at about that in the current context itself, locally as well. This is not about faraway places. WHO has a really interesting kind of a criteria. It's called the assured criteria. We'll pick this up in the next class, but it's an important scenario that if you're developing a test, when you're writing your functional requirement, these are requirements that WHO kind of recommends for the classes of tests that are more broadly accessible. And again, it is, it's been something that was developed over a long time. There is another list that we'll share with you all, which is now called the Essential Diagnostics List. So this is another list from WHO, just like essential drugs, that what is a minimum number of drugs every health center should have. And that's actually quite powerful to look through, and you'll see majority of them are still not available. Similarly, a couple years ago, they released a minimum number of diagnostics that should be widely available. And then that would be a great place to start. You might say, look, HPV testing. I mean, it's a massive storm coming when you see cervical cancers rising around the world. We have vaccines that people are developing, but we have no tests. We have no affordable test in majority of places around the world, and you cannot just roll out if you don't understand the prevalence of a disease itself. So, that's just one tip of the iceberg. There's thyroids, massive number of scenarios where just very, very simple tests could actually make a difference. So I'll share some of those lists, especially now if some of you are interested in working on health as a project. It would actually be very valuable to start on the other spectrum, not on the technology, but on here is a gap that I see that I'm excited about. Okay, I'm going to stop here. We will pick up on Thursday. If people have questions, we can have a few minutes of open time. I will share Wednesday's tomorrow, right? Okay, I'll share tomorrow time slots. If anybody wants to sit down, if you already have a project mate, you can bring along. If you don't as yet have a project mate, we can also do them on Zoom. We can do them offline. On Discord, we'll just share a Google Sheet, half an hour time slots for projects. This is true for just everybody that's also listening online too. Try filling this. It's much better to do it if you join as a team rather than just individuals. So if people have started building teams, it'll actually be useful. And then we'll pick it up. I see that the paper has dried, and one of them shows the phenomena that I wanted you all to see. It's not completely dry, but the thing that I wanted you to see, it's hard to see when you look from the top, but it's actually twisted. You see that there is a curl along this axis? So I'll let you all see this one more time, that there is a slight twist. And if I make it longer, you'd actually see that a paper, when it dries, it twists. And the question is why? Okay, so think about it. And try running this with newspaper. Then you really see these beautiful curls appear just naturally. You have to wet it, dry it, and you'll see a twist. So the paper that I had dried has actually twisted at this point. Try doing this with longer and longer strips of paper so you'll see the twist very clearly. And the question to think about is why. So do this as a very long stripe if you want to see the angle of rotation. Yes?
I don't know if this is why, but I think the curly hair.
Curly hair is a great place to start. Why does hair curl? Uh-huh.
And it's like pop.
Uh-huh. Yeah, yeah. Yeah, yeah. So, I mean, something about again, I want you to think about the microscopic property to macroscopic behavior. There is something about the microscopic property of this material, which is actually molecular. That's the hint. That you are seeing display out in a very macroscopic form. Yes.
Yeah, I was gonna say
Yeah.
something with curly hair.
Yeah.
I think like if you have curly hair, and I guess it's like the strands grow like in different.
Uh-huh.
speed.
Uh-huh.
So I'm guessing because you have
Yeah.
like cellulose chain,
Yeah.
maybe you have more shrinkage and like
Uh-huh.
of like one.
Yeah. Yeah. Okay, I'm going to let you guys think about it. Think of an answer and post on Discord. Why do you think this curls? And remember, you can't Google it, you can't read it, otherwise you've spoiled it for yourself. You're not going to enjoy the process of figuring something out. So just try to think how many different ways you can come up with why this curls. I'm going to say bye, and we'll catch up tomorrow. I see, Mrinal, you have your hand. Go ahead.
Yeah, Manu, I think me and Meg will be working on with like the team in Ethiopia at FHI 360.
Yes.
Like, yeah, we were working on a problem related to malaria in like the rural health posts. So the rural health posts, and we were thinking about implementing Octopi there, and we were talking to the team there, and they seemed pretty enthusiastic about that.
Yeah, I mean, I think that would be straightforward. I would be super excited. Let's do a Zoom call. Tell me which day this week or next week we can have you all the team members and the Ethiopia team join in, I can put together a deck to just show them what we have. And I think the field implementation would just be absolutely fabulous. Currently, one of the big limitations is we're not doing speciation. So I want to choose sites in which they have more than falciparum. But in general, getting it in a field where we are doing validation with community health workers would be my dream. And I think I have lots of partners in Ethiopia. It's the right place to implement because their health system really works. I mean, it really is quite rigorous, and it's just choosing and identifying the right set. And both of you have spent some time in Ethiopia. I would be so excited.
Sure, we had the basic discussion after we send you the mail. So they were talking to us that they do have some issues in the rural health posts where during the malarial season, because the RDTs have a low sensitivity, people don't trust it. So they just go to the health centers where they have RDTs and microscopy. So health posts just have RDTs, so they don't go to health posts, and the health centers get crowded, and it's a very messy situation.
Let's do a Zoom call. You know, I can do as soon as Friday, but I can do any time next week as long as it's outside the teaching time. So on Discord, let's just chat.
Sure.
Yeah, can
I'll
you
get
send
to
me?
them and
Awesome. Yeah, I'm excited.
Sure.
Yeah.
Me too. Yeah.
And then tomorrow I'll post a Google Sheet. Anybody who wants time, we can sit down and chat. It's best if you have 1 or 2 members that you have recruited, because then it's useful. You have somebody to bounce ideas with. And I think the same goes for everybody. But by Tuesday, we must have a team, even if you don't have a project, because projects will come. I want you to feel that you are bouncing ideas with somebody and spending time thinking, because we're halfway mark. I don't think we'll make anything unless we get started now. Does that sound good? Yeah? Are you excited, scared? Okay, all right. On that note, bye everyone.
Bye.
So hope I have to run. Yes.